Good morning friends, my name is Ganesh and we are going to learn about self-organizing maps SM, also known as Kohonen maps. It is a type of artificial neural network which is also inspired from biological models of neural systems from 1970s. It follows an unsupervised learning approach and trained its network through comparative algorithms. SOM is used for clustering and mapping techniques. SOM has two layers, one is input layer and other is output layer. So what are the principle of self-organizing maps? One is competitive learning, topology order and neighborhood functions. What is competitive learning? SOM employ competitive learning where neurons or nodes within the maps compete to respond to input patterns. When presented in input patterns, the neurons with the weight vector most similar to the input is considered the winner or the best matching unit, that is BMU. This winning neuron then updated its weights to become even more similar to the input pattern. Now, what is topological order? SOM preserves topological properties of the input space in the output space. This means that neighbor neurons is in the SOM grid represent similar input patterns. During training, not only does the winning neuron update its weights, but also its neighbor neuron in the SOM grid with decreasing intensity as distance from the winner increases. This topological ordering allows SOMs to provide insight into the structure of input data, revealing relationships and clusters that may not apparent in the original high dimensional space. Now, what is there is a principle of SOMs like unsupervised learning. SOMs are typically trained in unsupervised learning manner, meaning they do not require label trained data. Instead, they learn by underlying structure of the data slowly based on the input patterns. This makes SOMs particularly useful for exploratory data analysis, for identifying patterns relations within the data without prior knowledge or supervisions. That is the advantages of SOM also. Now, how SOM works, self-organizing map works. First, there are the phases like initializing, training, competitive learning, adapting, then topology presentation, then final presentation. So what is initialization? A SOM consists of grids of nodes often arranged in two-dimensional lattice. Each node in the grid is associated with weight vectors of same dimensionality as the input data. Now, in the training, SOM use unsupervised learning, meaning they don't require labeled data. During training, the weight of the nodes are adjusted based on the input data. The SOM algorithm iteratively update the weight in such a way that neighbor nodes in the grid become similar to each other if they respond to similar input. This process continues until the converging of or until a maximum number of iterations is reached. Now, competitive learning is done. In each iteration, SOM select the nodes whose weight vector is most similar to the input vector. This node is known as winner or best matching unit, that is BMU. I have said it earlier. Now, in the adaptations, after selecting the BMU, the weight of the BMU and its neighbor nodes are adjusted to become more similar to input vector. The extent of adjustment decreases with increasing distance from BMU, which encourage neighbor nodes to learn similar representations. Now, topology preservations. One of the key properties of SOM is topology preservations, which means that spatial relationships between input data point are preserved in output space of maps. This makes SOM useful for visualizing high dimensional data in the lower dimensional space while maintaining the inherent structure of data. After the topology preservations, the final representation is we comes to the final representations. Once the training is complete, each nodes in the SOM grids represent a clusters of or groups of similar input vectors. These clusters can be visualized on a map, allowing for easy interpretations and exploration of the data. Now, what are the exceptions in self-organizing maps? One of the exceptions is high dimensional data. SOM may struggles with high dimensional data due to curse of dimensionality. Now, second is outliner. Extreme outliner can signify impact of map topology and cause distortions. Now, irregular clusters. Clusters with non-uniform density may pose challenges for SOMs to represent accurately, and there are many exceptions. You can refer on the internet or any sites. What are the advantages of self-organizing maps, SOMs? SOMs offer several advantages, making them a popular tool in various fields of data analysis and machine learning. Some of the key advantages of SOMs include dimensionality reductions. SOM can reduce the dimensionality of complex data, which while preserving the essential relationships and structure present in the original data. This reduction in dimensionality facilitate visualization and interpretation of high dimensional datasets, allowing analysts to gain insight into the underlying patterns and cluster. Now, topology preservations. SOMs preserves the topological properties of input space in output space. This means that neighbor nodes of the SOMs grid represent similar input patterns, enabling intuitive visualization, interpretations of data cluster and relationships. Topology preservations help maintain the integrity of data's spatial structures, which is crucial for understanding complex datasets. Now, ease of interpretations. The visual representations generated by SOMs makes it easy to interpret and analyze complex data structures by mapping high dimensional data onto two-dimensional grid. SOMs provide a concise and intuitive representation of data, allowing analysts to identify cluster trends relationships at a glance. This interpretability is valuable for communicating insight to stakeholder and making data-driven decisions. Now, advantages based on unsupervised learning. SOMs are trained in unsupervised manners, meaning they do not require label training data. If there is no label training data, then also we can apply SOMs. This makes SOMs particularly useful for exploratory data analysis, as they can identify hidden patterns, structures within the data without prior knowledge or supervisions. Unsupervised learning is also allows SOMs to handle large data set with minimal human interruptions. Now, clustering and visualization. SOMs can effectively cluster input data based on similarity, grouping similar data points together on SOMs grid. These clustering capabilities enable tasks such as data segments, patterns, recognitions, and anomaly detections. Additionally, the low dimensional representations provided by SOMs facilitate visualizations of complex data sets, aiding in data explorations and decision making processes. Robustness to noise and outliers. SOMs are relatively robust to noise and outliers in input data. Due to their competitive learning mechanism and neighbor-based updates, SOMs can adapt to noisy and incomplete data without signifying affecting the overall performance. This robustness makes SOMs suitable for handling real-world dataset with varying levels of noise and uncertainties. What are the limitations of self-organizing maps? While self-organizing maps offer various advantages, they also have certain limitations that users should be aware of. Some of the limitations are interpretability of grids. While SOMs provide visual representation of high dimensional data in lower dimensional grid, interpreting the resulting maps can sometimes be challenging, especially for large and complex dataset. Understanding the relationship between the neurons on the grids and their corresponding input data may require additional analysis and domain knowledge. Choice of parameters. SOMs performs can be sensitive to choice of parameters such as grid size, learning rate, and neighborhood function. Selecting appropriate parameters often requires empirical testing and tuning, which can be time consuming and may not allow guarantee optimal result. Computational complexity. Training a SOMs can be computationally expensive, especially for large dataset and high dimensional input spaces. Such as the size of the grid and complexity input increases, the computational requirements of the SOMs algorithm also escalate, potentially limit its scalability and applicability to large scale problems. Overfitting and generalization. Like other machine learning models, SOMs are susceptible to overfitting, where models learn to memorize the training data rather than generalize unseen data. Overfitting can occur if the SOMs grid is too large relative to dataset's size, or if the training data process continue for too many iterations. Initializing sensitivity. The initial configuration of SOMs grid can influence the final maps of clustering outcomes. Random initialization may lead to different results in multiple runs of the algorithm, makes it challenging to ensure reproducibility and consistency across experiments. Limited supervision. SOMs primarily rely on unsupervised learning, meaning they do not utilize label training data to guide the learning process. While this allows SOMs to discover intrinsic patterns and structure within the data, it may also mean that they may not leverage potential use of supervision information if available. Means if there is useful data and if we can use it, then there means leveraging the potential of useful supervision means may not be used to that level or to that extent. Applications of SOMs related to image recognitions means there are many applications of the SOMs. So few of them are image recognition, market segmentations, neuroscience. Image recognition. SOMs can be used for feature extractions and dimensionality reductions in image processing tasks. They help in reducing the complexity of image while preserving important visual patterns. In the context to object recognition, SOMs can categorize image into different classes based on their visual features. SOMs have been employed in facial recognition systems to detect and classify faces in image. In medical imaging, SOMs assist in identifying patterns and anomalies in various types of scan, such as MRI or CT scans, aiding in diagnosis and medical research. SOMs means like in markets, second applications of the SOMs is market segmentations. SOMs are utilized to segment customers or market data in distinct groups based on similarities in their characteristics or behavior. By clustering customer into segment, business can better understand their target and audience, tailor marketing strategy, and develop personalized products or services. SOMs helps in identifying market trends, uncovering hidden patterns in consumer data, and making data-driven decisions to improve sales and profitability. Market researchers use SOMs to analyze survey data, identifying consumer preference, predict market trends, enabling companies to stay competitive in dynamic market environment. Neuroscience. SOMs play a significant role in analyzing of brain activity and neural network. In neuroimaging studies, SOMs help in clustering and visualization patterns of brain activity captured through techniques like fMRI. fMRI means functional magnetic resonance imaging, or EEG. Sorry, I am unable to pronounce it, so you just refer it. SOMs aid in mapping the organization of cerebral cortex and understanding how different regions of the brain process sensory of information or control motor function. Researchers use SOMs to model neural network and study complex phenomena such as learning, memory, and neural plasticity. SOMs are employed in bioinformatics to analyze genetic data, classifying gene expressions patterns, and identifying gene regulation network associated with neurological disorder or cognitive functions. That's all for me. Thank you.